Welcome to the next video, and we're going to analyze quadratic functions in Vertex form today. So I want you to graph the following into Desmos. These four different graphs, graph them into Desmos, and then we're going to compare to see what they look like. So I've done that here already. The blue one is x squared. The green one is 2x squared, the purple one is 3x squared, and lastly the black one is 4x squared. So if you look at the shape of our graph, it seems like we are getting narrower and narrower. So that's what happens when you put a coefficient in front of x squared, it just becomes more narrow. So we can state that here, that in terms of the appearances, the width becomes more narrow, and your direction of the opening is still up, where your arms are facing up. I want you to go ahead and try part 2, 3, 4, and 5 of this activity, and then fill in the conclusion at the very end. So here's part 2. Once you graph this into Desmos, you're going to see that instead of getting narrow, it's going to get wide. So you can probably conclude that whenever you have a fraction that's smaller than 1, it's a proper fraction, in front of your x squared, you are going to have a wider looking parabola. And the direction of this opening is still up because your arms are facing up. For 3, we're going to manipulate now in 2 ways. From x squared to 2x squared, it looks like we're going to have a more narrow parabola. But the direction of the opening will change if you have a negative in the front. So your direction of opening is down with the negative in the front, and it'll be up if you have no negative in the front, so just a positive number. For part 4, if you keep adding or subtracting numbers at the end of your x squared, we're going to move a parabola up and down. And we're going to move up and down according to that number. So for x squared plus 2, you moved up 2. For x squared minus 3, you're going to move down 3. Then for part 5, if you add a number inside the bracket of x, then you're going to move the parabola left or right. So all these parabolas are not the same, but they share a similar shape. And you could have written some rules down, but I'm going to tell you the actual rules of how we're going to analyze all these quadratics in vertex form on the next page. Okay, so the A, the number in the front, this represents your width of the parabola. So it stretches or compresses your parabola, and the direction either opens up or down. It'll open up if your A is positive, and it'll open down if your A is negative. So if A is greater than 1, if you have a number like 2, 3, 4 for your A, the graph will be more narrow. If you have a proper fraction, so some sort of fraction that's between 0 and 1, the graph will be wide. Here's some examples where A is equal to 2, or 5, or 10, or so on. And look wide if A is equal to a half, a quarter, a third, and so on. If A is smaller than 0, that means A is negative. The graph will be upside down, or look like this. Now the P that's inside the bracket, this shifts the graph left or right, so that's your horizontal shift. If P is positive, the graph will shift to the right. If P is negative, the graph will shift to the left. So for example, if you had x minus 2, your p-value is 2, so you're going to shift 2 to the right. Now, if you had a positive number here, let's say something like that, p is equal to -1, because this would be x minus -1 to get x plus 1. Since p is negative, we're going to shift to the left. So shift 1 to the left. And lastly, for q, the number that's outside of the x squared, this represents the vertical shift of your graph. So that means if q is positive, the graph will shift up, and if it's negative, it'll shift down. And together, PQ is the position of your vertex. That's very important. Okay, so let's try this out with just the basic graph. So y equals x squared. Your domain is going to be always negative infinity to positive infinity for all quadratics. Now your range depends on where your vertex starts. In this case, our vertex is 0, 0, because that is our base function. You should have this graph memorized by now because this is the basic function for your quadratic. I'm just going to label the axes a bit here. Okay, and then your next point should be 1, 1, negative 1, 1, 2, 4, negative 2, 4. If you don't have this graph memorized, you can always use a table of values to figure this out as well. But I really suggest you memorize this basic graph. Now for your range, that's the lowest y value to the highest. So our lowest y value possible is 0, and we touch it. Then your highest y value goes towards infinity. You don't have a particular value. Your axis of symmetry cuts down right in the middle. So it looks like that. This is x equals 0. Remember to express this as an equation. Your vertex is down here at 0, 0. This is also your minimum because whenever you have a graph that looks like this, it has a minimum value. And this occurs at x equals 0. Your x-intercept is at 0, which is where your vertex is, and your y-intercept is also at 0. So your graph touches the x-axis at x equals 0, and your graph touches the y-axis at y equals 0. So that is our parent function. Now we're going to look at some transformations of this vertex form graph. Okay, for this next part, we are going to graph y equals x squared plus 1. This plus 1 means that we're going to shift up 1. From our parent graph, which is this one, y equals x squared. So you're basically moving all those points just up 1, and that's what we're going to do. Okay, so our vertex used to be 0, 0, but then we're going to move up 1. So now it's at 0, 1. We had a point here at 1, 1. We're going to move that up 1. Now it's at 1, 2. Symmetrical, so same on the other side. And then lastly, we had a point at 2, 4. And now it's going to be at 2, 5. And symmetrical, so we have the same one on the other side of our y-axis, and this is our graph. Another way you could do this is read out the vertex from here. So we don't have anything inside the bracket. So equivalently, I could write it like this, it doesn't change. And if I were to read off the vertex here, it would be 0, 1. So that number inside would be 0. That determines your x coordinate, and your y coordinates on the outside, which is at +1. And that's the vertex we drew. And then from there, you could also do a small table of values to find one more point. For example, you could have put x equals 1 into our equation and we would have gotten 2 anyway. And then you know you're going to get the same one on the other side. So you could do a mini tables values from there after you get the vertex. So that's another method. Now finding the domain, from left to right, our values could be anything. So it's negative infinity to positive infinity. Again, it's a parabola, so it always has the same domain. For your range, your lowest y value is 1 and we touch it. Highest goes to infinity. Your axis of symmetry cuts right down the middle of your parabola. Looks like it's located at x equals 0. We have a minimum, and this occurs at x equals 0. We don't have any x-intercepts, so you can just say none. But your y-intercept is located at y equals 1. That's where we cross the y-axis. Go ahead and try the next one. This time we're going to move down by 2. So you're going to look at your parent function, y equals x squared, and move it down by 2. So here's a solution to that. I just took the parent function and then moved all the points down by 2. And this is the graph we get. So now we have a vertex at 0, -2. Your axis of symmetry is at x equals 0. Your range is now from -2 to infinity because that is your lowest y point. Domain doesn't change. Your minimum is still at x equals 0. But your x-intercept, you have to set y equals to 0 and then solve for x. So then you move the 2 to the other side and square root both sides. This becomes plus or minus √2. Then lastly, for your y-intercept, we cross the y-axis at -2. Moving on to the next example. Now we're doing a shift from here, and this means you're going to move left or right. Because this is a positive, this means that we're going to move to the left 1. Because in the format, it should be x minus 1, and that would give us x plus 1. So because it's negative, we're going to move to the left. It's negative here, so we're going to move to the left. In other words, you can think if you see a positive inside the bracket, then you're moving to the left. So from our parent function, we used to have a vertex of 0, 0. Just going to move it 1 over to the left. Now it's at -1, 0. Then I'm going to move all the other points from our parent function over to the left by 1. We used to have a point at 2, 4. Now it's going to be at 1, 4. And it's symmetrical, so we have to make sure on the other side of that, at x equals -3, we have that as well, at 4. And that would be your graph. So your domain doesn't change. Your range is going to be from 0 to infinity because your lowest point is at 0, y equals 0. Axis of symmetry now is at x equals -1, which is your x value of your vertex. Your vertex is at -1, 0, which is this point here. You have a minimum at x equals 0. Sorry, x equals -1, not 0. We just shift everything over to the left by 1. And then your x-intercept is at -1. That's where we cross the x-axis. And we cross the y-axis on this point here. So that's y equals 1. So try the next one on your own, and then when you're ready, press play. Okay, so for this next one, we're moving everything to the right by 4. In other words, your vertex is going to be located at 4, 0. So you can take your parent function and move everything to the right by 4. So your vertex is now at 4, 0. You had a point at 1, 1. Now, once you move it forward to the right, it's at 5, 1, and so on. So your domain is negative infinity to positive infinity, doesn't change. Your range is from 0 to infinity. Your lowest y value is 0. Axis of symmetry now is at x equals 4. And you have a minimum there at x equals 4. Your x-intercept's also 4. That's when we cross the x-axis. And then you need to find the y-intercept. In this case, you could just set x equal to 0 and then solve for y. So then you're going to get negative 4 squared. And that negative's inside the bracket, so that's negative 4 times negative 4, which is positive 16. Okay, for the next one, this is a stretch or compress. This will make our graph either wide or narrow. In this case, because our number is 2, this is a whole number that's larger than 1, we're going to get a more narrow graph. So our vertex here is still at 0, 0, because we don't have a number on the inside, nor do we have a number on the outside. So that's where our vertex is located at. If you want to find the next point, the easiest way to do this is to do a mini table of values on the side. So let's just say we want to figure out another point at x equals 1. Then I'm going to plug this into our function. That's 2 times 1 squared, which is 2. So then my next point is at 1, 2. Since this is our vertex 0, 0, on the other side it has to be symmetrical, so I know there's a point here as well. Now we can just connect these points and extend a bit, and that would be our graph. So your domain for this is the same, negative infinity to positive infinity. Your range is from 0 to infinity. Your lowest y value is 0. Your axis of symmetry is the x value of your vertex, which is 0. We have a minimum here at x equals 0. Your x-intercept is 0, and also your y-intercept is at 0. So try the next one on your own. Similar type of concept, but in this case, our graph is going to look wider in comparison to the original function of x squared. And then you could do a mini table values on the side to figure out another point. Okay, so here's the answer to that try it yourself question. Again, our vertex is going to be at 0, 0. On the side, I did a mini table values to figure out my next point. In this case, I plugged in x equals 2. You could have picked any other number, like 1. I just picked 2 because I wanted a whole number out of it. So if you put in x equals 2 in the function here, that's 2 times 2, because it's x squared, which is 4, and then multiply it by half, then you get 2. So you have a point at 2, 2. We know symmetrical, so you can have a point on the other side of your vertex at negative 2, 2. Connect those points, extend a bit, and add arrows, and you're done. So your range is from 0 to infinity. Your axis of symmetry is at x equals 0. Your x-intercept's at 0, and your y-intercept is also at 0. For our last example, now we have a negative in front of our x squared. This means our graph is going to be upside down. And our vertex is again going to be at 0, 0, because if you read it off, this is the same thing, and this determines our vertex. Now usually our parent function would go up, and now we're going to have the same sort of thing, but everything's going to face down. So before we had a point at 1, 1, now it's going to be at 1, negative 1. And at negative 1, negative 1. Before we had a point at 2, 4, Now we're going to have a point at 2, -4. And -2, -4. So this is what our graph looks like. And if that method is not your favorite type, that's fine. You could have done a table values on the side as so, and picked 1 as your x value. That's -1 squared. So the negative's outside the bracket, so that means the negative is still present. So your new value is 1, -1, which is the point we had. So you could have done a mini table values on the side if you wish, but I would rather you memorize your parent function, which is y equals x squared, and then just know that everything will be flipped downwards. So all your y values become negative when this happens. So your domain is the same because we can have any x value. Your range, though, is going to go from -infinity, because we don't know what the lowest y value is, to the highest point, which is 0. Your axis of symmetry is the same as the x value in your vertex. In this case, we have a maximum at x equals 0. Your x-intercept is at 0, and same with your y-intercepts, also at 0 because of that vertex of 0, 0. So that's it for graphing for quadratics in vertex form. Go ahead and try the homework that has been assigned.